everyone. Previously, we have discussed the existence involved in the division algorithm. In this video, we prove the uniqueness of the division algorithm. Let us also try the proof by contradiction. Assume to the contrary that for some integers a and b, we will be able to find two pairs of integers, say q1 and r1, q2 and r2, that they both satisfy the desired equality. From there, we can put all terms with b to one end and all terms without b to the other end. This gives the equality b times q1 minus q2 is equal to r2 minus r1. What can be the value of r2 minus r1? Let's try to estimate this value. Well, recall that r1 is greater than or equal to 0 and is strictly less than b. Multiplying -1 everywhere, this gives negative r1 is less than or equal to 0 and is greater than negative b strictly. Similarly, r2 is greater than or equal to 0 and is strictly less than b. We copy this condition as it is. Now, adding these two inequalities together, we see that r2 minus r1 is strictly less than b and is strictly greater than negative b. Now, let us replace r2 minus r1 by b times q1 minus q2. And the inequality becomes b times q1 minus q2 is strictly less than b and strictly greater than negative b. Again, using the fact that b is a positive integer, we divide b everywhere. This shows q1 minus q2 is strictly less than 1 and greater than negative 1. But what can be the integer that is strictly sitting between -1 and 1? We don't have any other choice but 0. Hence, q1 minus q2 is equal to 0. In other words, q1 is equal to q2. Now, plug in this equality into the previous condition, we see that r1 is also equal to r2. That finishes the proof for the uniqueness. Alright, now you have seen the division algorithm. In the coming section, we will study the greatest common divisor, and we will soon see how the division algorithm, when applied repeatedly, can help us compute the greatest common divisor for an arbitrary pair of given integers.